we will now define asynchronously realizable graphs. So we say that the state S is stable for the input I if the next state function that takes as input the state S and the input I is the same state S. So in our graph, this means that if we have the input I, this gives an edge back to the same state S. And related to this, if there is a path for the input I from the state that we call S0 to the stable state S, then S is the successor state of S0 for this input I. And this leads us to the definition of an asynchronously realizable graph. So we say that a graph is asynchronously realizable if all the states have a successor state for all the inputs. So let us look at an example of this. So let's say we have a graph with 4 states. We call them S0, S1, S2, and S3. Being asynchronously realizable doesn't have anything to do with the output, so I will just disregard from the output when I write our state transition graph here. So from S0, if we have the input 0, we go to S1. If we have the input 1, we go to S3. From S1, if we have the input 0, we stay in S1. And if we have the input 1, we go to the state S2. For S2, with the input 0, we stay in S2. And with the input 1, we go to the state S0. And for S3, with the input 0, we go to the state S2. And with the input 1, we stay in the state S3. So let's first consider the definition for a stable state. So a state is stable if it for an input I stays in the same state. So we can see here that S1 is stable for the input 0. Because here in S1, we stay in S1 with the input 0. Similarly, S2 is also stable for the input 0, because we see here that if we have the input 0 and we are in S2, we stay in S2. And we can also see that S3, this state is stable, but for the input 1 in this case, because we here have with the input 1, we stay in the state S3. However, the state S0 is not stable for any input. Now let us look at our successor state for the different state. So we enumerate our different states for the different inputs that we have, and then we see what is the successor state. So what we'll do here is that we will write each of the states and each of the inputs. So S0 can have input 0 or 1, S1 can have input 0 or 1, S2 can have input 0 or 1, and S3 can have input 0 or input 1. Now let us look at our successor state for each state and input. So let us start with the first state S0 and input 0. If we are in S0 and have the input 0, we go to S1 and then we stay in the stable state S1 because this is stable for the input 0. So S1 will here be the successor state. If we have the input 1 instead, we will first go to S3, but S3 is stable for the input 1, so S3 will here be our successor state. For S1 with the input 0, we just stay in the state S1, so the successor state here is S1. If we get the input 1, we first go to S2, then we go to S0, then we go to S3, and then we stay in the stable state S3, which is stable for the input 1. So here the successor state will be S3. For S2 with the input 0, we stay in S2, so this will be our successor state. With the input 1, we will first go to S0, then to S3, and then we stay in the stable state S3. So this will be our successor state for S2 with input 1. For S3 with input 0, we first go to S2 and then we stay in S2. So S2 here is our successor state. And if we have the input 1, we just stay in the state S3 because this is stable for the input 1. And since all states have successor states for all possible inputs, we know by definition that our graph is asynchronously realizable. Let us also see an example of a graph that is not asynchronously realizable. So we look at a similar graph that we had before with 4 different states, S0 to S3. With a 0 we go from S0 to S1, and with a 1 we go to S3. From S1 with both a 0 and a 1 we will stay in the state S1. From S2 with a 0 as input we go to S1, and with a 1 as an input we go to S3. And from S3 with a 0 as an input we go to the same state S3, and with a 1 as an input we go to the state S2. And what we can see here is that if we have S0 and the input 1, it means that we go from S0 to S3, and then we go back and forth between S2 and S3. So we do not reach a state that is stable for the input 1. So S0 with the input 1 has no successor state. And similarly, both S2 and S3 with input 1 does not have a successor state because it doesn't reach a stable state for the input 1. So we can also say that S2 with input 1 and S3 with input 1, all these combination have no successor state. And according to the definition, all the states for all inputs needs to have a successor state in order for our graph to be asynchronously realizable. So this graph here is not asynchronously realizable.